So in this session, we are going to explore pattern transfer. In the previous lectures, we discussed about how to transport material onto the surface. But in this particular series, what we are going to look at is how do we make patterns, right? So what I mean by patterns, right? So let's look at the patterning. Right? So far. We took a substrate. It can be silicon or silicon dioxide, any kind of substrates, and then we deposited a material. It's a blanket material, right? So this could be you know conducting or insulating, so it can have multiple properties. So however, this material is continuous, right? So this is cross section. So if I look at top down, I will not see any profile. It's going to be flat, right? But if you want to make any kind of meaningful circuitry, you want to make either electrons or photons or any other form of energy to flow in particular direction. So if you take a thin film like what we see here, the conductivity is going to be throughout this layer, but what we actually want is to restrict the flow, right? So so if this is a metal, so what we want is restrict the flow only within this cross section, right? So now I have only conduction in this part where the absence of material makes it insulating in the other part. So from top down, it will look something like this now, right? So if you are going to measure if you are going to put any a field or a potential across, so the direction of your electron flow will be here, but in this case it can take multiple paths, right? So what we are trying to do here is to restrict the energy flow, right? So this is what we call pattern transfer, right? So from a continuous film to a restricted cross section where you can exploit this for whatever functionality you want to realize, right? So pattern transfer can be classified into two broad categories. One is direct transfer. So one is direct pattern transfer and the other one is indirect pattern transfer. Those are all the two broad classifications. Okay, so what do we mean by direct? So direct meaning if I take a film, right, and then I can directly make the cross section, right? I don't need any intermediate layers, so I can directly pattern whatever substrate or whatever material that I want to pattern. I can do that patterning. But in indirect, I will use an intermediate layer, right, to transfer the pattern. So first I will transfer the pattern to this intermediate layer and then I will transfer it to the subsequent layer, right? So this is how I do intermediate patterning, right? So that is the major difference between direct and indirect patterning, right? So within direct patterning method and indirect patterning method, we have a subdivision, right? It's a subdivision of writing and printing, right? Both in direct, we also have it in indirect. So what do we mean by writing? So writing is as simple as the way we write, right? So the way we write is a serial process. So you take a pen, right, and then you start writing. So it's a serial process. You don't write multiple words in one go. So each letter by letter you start populating, right? Similarly in pattern transfer, we are going to write this pattern bit by bit, right? So if you have a n number of structures, you are going to write one by one, and for that we can use iron milling process, iron implantation process, or you can also use laser writing. So all these processes are serial. Okay, and on contrast, we have printing, right? So printing is a parallel process. So here we can do imprint patterning or mold patterning. So for most of you, this imprint patterning might be more familiar. So this is nothing but taking a template, right? So and then using that template to print pattern on, the way that we print cloths, right, for example, or the screen printing, right? Screen printing is a good example of direct printing technique, right? So imprint is one. The other one is mold, right? So molding, like the way that we do bricks, right? So brick molding. So we already have an existing mold, and then we fill up the material, and then whatever material that we fill up take the shape of the mold, right? So those are all the techniques that comes under printing, right? So let's look at indirect patterning, right? So in indirect patterning, as I mentioned, this is beam. So where we are going to take an energy, either electron or photon, to pattern an intermediate material, right? And then the pattern from the intermediate material is transferred to the substrate. So here there is electron beam lithography and there is optical lithography. So in electron beam, we are going to use electrons, right, to transfer the pattern onto this intermediate layer. In indirect patterning, we are going to use optical. So electron beam, right, the beam itself should give you a clue that it's a serial process, it's a writing process, right? I have a pencil of beam and I am rastering it over the substrate that I want to pattern, right? And then in indirect patterning, I'm taking optical lithography or optical technique. So as we all know, optical technique, it can be either, writing. We can also have parallel processing, right? And in this case, printing. And within optical, we have contact litho and projection litho, right? So we are going to see these contact litho and projection litho in detail in subsequent sessions. But within this understanding of pattern transfer, these are all the two techniques that is available for us. And finally, we would like to look at the CMOS compatibility of this process. So what is CMOS? Complementary metal oxide semiconductor technology. It's a technology platform. Whether these techniques can be used in CMOS fabrication or device fabrication. So mostly, if you can broadly see, this writing processes are very slow, right? Unlike printing. So that's why we don't use this writing primarily, because you won't be able to get the throughput that you're looking for, and also perhaps the resolution in some cases as well. Direct printing, right? So direct printing is something that is being was explored for advanced patterning, right, beyond 10 nanometers or so, and electron beam lithography as well. So though it is a writing technique, later on in the lecture we will see that it's interesting modifications that you can bring in to make this writing process, right, parallelized writing process, where you will be able to get a reasonable throughput. And indirect printing process. So this is the majority of patterning is done in this. To be precise, projection lithography is what is used predominantly, but lately for a lot of advanced integration techniques, back-end integration, contact lithography is also used. So overall, for large volume manufacturing, this indirect printing technique is primarily used, right? While this writing process is used for primarily R&D type of work, and here this is used for manufacturing, right? The other techniques, the direct printing and these things, are also primarily used for R&D purposes. where people are exploring these techniques for various applications, not necessarily for electronics. It's, for instance, direct printing and direct writing are explored for bio applications, right? MEMS type application, and many more, right? So that's primarily the available techniques that we have in pattern transfer. So lithography, as I mentioned, is one of the most sophisticated process. If we look at the CMOS technology evolution, right? If I have to give you just a brief idea. So if this is year and this is transistor dimension, right? Over the years we saw decrease in the transistor dimension, right? So we started from 1 micrometer technology, and now we are at 14, less than 14 nanometer node, right? So the whole this revolution is primarily driven by lithography, right? This is all about reducing the size of the transistor, right? This is what has happened, right? So lithography became a very, very important part of micro and nano fabrication technology, and that's the reason why we say it is sophisticated and it is very critical, and because of nature of the process it is also very expensive, and that can actually be half of the cost of total fabrication itself, right? So it adds a technology to miniaturization, but on the other hand it also add cost, right? And any a single mask set or circuit fabrication, a functional circuit fabrication can take up to 30 to 40 masks, right? So what do we mean by mask? Is nothing but a single layer of patterning requires this mask, right? So there are 30 or 40 layers that you have to use in order to make any functional circuit, right? And the cost, as I mentioned, each mask set can cost, mask alone costs about 1.5 lakh US dollars, right? So this actually increases as you move from lower mask technology to higher mask, right? So the functionality and sophistication increases, but at the same time cost also increases. So we saw the importance of pattern transfer. So now let's look at why or how this direct patterning and indirect patterning is done. So how are we going to transfer a two-dimensional structure into a three-dimensional structure onto the wafer, right? So when you imagine a circuit, we imagine in a two-dimensional fashion, or even we draw these structures in two dimension. But how do we transfer this onto the wafer, which is going to be a three-dimensional feature, right? So in direct patterning, we use a scribe, right? The scribe can be physical or chemical, right? So when I say physical, this can be a hard tip, right? So this could be a solid tip, right? For instance, it is made of let's say silicon, right? And then you can apply pressure onto the substrate and start removing the material. So when you remove the material, you start profiling the surface, right? And this profiling the surface can result in pattern transfer. So this is one way of doing the transfer. So you can use AFM tip, right, to do this pattern transfer if you apply enough force. And then you can for the chemical, you can use some ion beam, right? So the beam has some ions, and this ion can actually react with the substrate or even physically transfer this energy and knock out some of these molecules and atoms sitting in the substrate, and during this process you are going to transfer the pattern. And the next way is to do using indirect patterning. So in indirect patterning, as I mentioned, we use an intermediate layer, right? We don't directly touch the substrate. The substrate remains untouched and pristine, right? Unlike the direct patterning case, where there is an interaction between the scriber and the substrate, in the indirect patterning technique, you don't have any interaction. So now the intermediate patterning, you use optical or electron beam in order to remove a part of this intermediate layer, and now this pattern will be transferred onto the substrate by using a pattern transfer technique, which can be etching, right? So here we are removing the exposed part, and that is what we call indirect patterning. First transfer the pattern onto this intermediate layer, and then you transfer that intermediate layer pattern onto the substrate that we have. So this is what we call indirect patterning. All right. So this is the contrast between direct patterning and indirect patterning, right? Direct patterning is a straightforward technique, right? So there is no need for any intermediate layer, right? There is no subsequent processing required. We just take the physical object or a beam to directly write onto the substrate. As I mentioned, it is a physical process, right? So by which we are removing it. So the resolution here is limited. What is the smallest feature we can transfer, right? That depends on the scriber, right? How small the scriber could be. This is similar to writing, right? If I give you a pencil and then ask you to draw a thinnest line, right? So the thinnest line can be drawn by using sharpest of your point, right? So you have to make the lead very sharp to draw very fine lines. Similarly, the scriber that you are going to use should be very sharp. So based on that sharpness, your resolution is limited, right? So this physical process is very destructive. So it's a destructive process, right? So that is the reason why it can result in some damage to the structure that you are actually defining, right? So a non-physical scriber, right? A non-physical scriber could give you a better resolution. For instance, an ion beam, right? So if I use an ion beam, right, and this ion beam can interact with the substrate and then pattern the substrate, right? And this is non-contact, right? And this non-contact techniques could yield slightly higher resolution. And we will see later on in the lithography lecture that the mass of the particle that you use has a direct influence on the resolution, right? So if you use ions, you can have better resolution. But still, as I mentioned, direct patterning, direct writing and patterning is not preferred because it is a writing process. So writing processes are always slow. So because you want to fabricate more number of devices, more number of circuits within a short period of time to increase volume, to increase throughput, these writing techniques are not preferred. On the other hand, in indirect patterning, we have resource intense process, right? This is because the direct patterning just used a scriber, right? In indirect patterning, you need to have this intermediate layer, and you need an exposure, you need some optical or electron beam, and then you have to remove this exposed part, and then you go for subsequent etching process, and then you have to remove this intermediate layer also, right? So there is multiple steps involved. So that's why it is called resource intense. And when I say resource intense, it also translates to expense, right? It also becomes expensive to make patterning using indirect patterning. However, this indirect patterning is preferred for the reasons that is listed in the subsequent bullet points. One of the other issues that we could face here is multiple process steps, right, will always result in some yield problems, right? So we have to make sure that you reduce the number of processing steps. When you increase the number of processing steps, each process step can bring in a yield reduction, right? So some failures can happen and we have to reprocess. So that is the reason why this multiple process is one of the disadvantages in this. So this is one of the widely accepted patterning technique. The reason for that is it is parallel, right? Despite having a number of process steps, it becomes repeatable and reproducible, right? So that is the next step. The flexibility and reproducibility wins over the resource that we need, and also the multiple processing that we have to do. So the reproducibility, which is very, very important, right, in any manufacturing process. So that actually makes this process win over whatever shortcomings or disadvantages that we listed above. And overall, the large volume manufacturing process, including the CMOS or any MEMS processes, uses indirect patterning extensively. So these are all some of the tools we use, right, for indirect pattern transfer. So ion beam milling, as I mentioned, we can use an ion beam in order to transfer the pattern, right, or use a laser, right. So we can use this laser, and if the material is photosensitive, in this case it's a photosensitive polymer, we should be able to transfer the pattern. Or scanning probe lithography. So as I mentioned, you can use a probe, right? It can be a physical probe that you can use to transfer the pattern, and then there are many more. During the later part of this lecture, we'll also see various indirect pattern transfer techniques. In direct transfer, as I mentioned, we use optical lithography. This is what predominantly used in industry for pattern transfer. Electron beam lithography, which is primarily used in R&D, but now being explored for next generation lithography, even in high volume manufacturing. Nano imprint lithography, right? So this is again an optical process, combination of optical and the thermal process, and this is again primarily used in R&D type of environment. And of course there are many more to list here. These are all few to give you an idea about the different type of patterning tools, right, rather techniques that one can use in order to realize the structures. And this is what the process flow for an indirect pattern transfer would look like. First, we'll take a substrate which has that has no profile at all, right? It's very flat. So now I want to make a pattern in this, right? How to do that? First, I'm going to coat it with an intermediate layer. In this case, we call it as photoresist, right? It's a soft material, and we can do spin on, right? So we can spin coat this. This is one way of material transport, right? So you can put this material in a chuck, and then you rotate this particular wafer, right? And then if you can drop cast this material, it will when you are spinning, it will spread, right? So I drop cast this, and then when I spin this wafer, this liquid, it's a viscous liquid, this is going to spin, and then it will uniformly coat on the surface, right? So we'll briefly look at how this spin coating work later on, but this is how you bring this material on top of this substrate, right? So once you have this viscous material on the substrate, you do a soft baking, right? So you put heat energy, right? So you bake this. So when you bake it, the solvent present in this particular material evaporates, making the material solid, right? And then once the material solidifies, we will use a stencil, mask, or photo mask, you can call it any way you want, put it on top of this material, and then illuminate it with light, right? So there is a light source on top. So this light source can be used to illuminate this layer, and this layer would prevent the light in this opaque region, and in this transparent region it will allow the light to go through, and whatever light that goes through this transparent region will make some chemical changes, right? So this chemical change will allow us to remove that particular material from that particular illuminated region, and then once that material is removed, I expose this substrate, and the exposed part can be removed using etching. So it can be either dry or wet etching. So we use either dry or wet etching process in order to remove this material. And as I mentioned earlier, we need to remove this intermediate layer, right? So this intermediate layer is used to just transfer the pattern. So once the pattern is transferred, we will remove that material, giving us the final product where we transferred a uniform or without any topography to a substrate with a pattern. So this is briefly how we transfer a pattern using indirect method, right? So this is a very a basic understanding of the pattern transfer techniques and the process that we do and the importance. And in the subsequent lectures we are going to discuss how optical lithography is used, and what is the importance of photoresist, the importance of light source, and the intermediate processes involved in achieving this pattern onto the substrate.